Hi everyone, today we would like to present our work on using a large language model for in-context student modeling and behavior synthesis with a focus on visual programming domain. In the last few years, we have seen a surge in the application of LLMs. They are becoming expert models in various domains such as pair programming, finance, text to video, and more. We explore how LLMs can be used for modeling students in tutoring system, which is crucial for personalized educations. A student is a learner who is not an expert yet, and their knowledge can be incomplete and buggy. Having a student model allows us to predict future learning outcome and design targeted feedback and instructions. However, accurately model a student in open-ended learning domain is challenging due to the diverse behavior and a large space of possible misconceptions. Given the same task, different students can have different strategy, different misconception, and different behavior. To approach this challenge, we explore the application of LLMs for in-context student modeling in open-ended learning domain. More specifically, in our goal is to use an LLM to model how a particular student solves a visual programming task, then synthesize the same student attempt on a target task. We demonstrate this using an example on this slide. First, in order to model a student, we need to give LLM some information about the student, which we call student context. And in this example, the student context is given by a triplet of a task called reference task, which is a grid with a blue avatar and a red goal. A solution code which bring the avatar to the goal when executed, and a student attempt on solving the task. The code written by the student is buggy, caused by the student misconceptions. At the same time, we give the LLM a target task, which is similar to a reference task, and ask it to generate a code which should reflect the observed student behavior and misconceptions. To this end, we introduce a novel framework that leverages LLMs for synthesizing student behavior in visual programming. The design of our framework is inspired by the perturbation student model, based on the idea that a student knowledge can be modeled as perturbation to expert knowledge. Therefore, having access to expert knowledge and a student misconceptions allows us to model the current state of the student understanding. Following such idea, we provide these elements to LM through fine-tuning and prompting with the student context. We need to provide expert knowledge to the LLMs because the LLM might not have been pre-trained on data coming from specialized domain we're interested in. Visual programming is an example. Existing work have shown that LLM can be tailored to specific domain through fine-tuning. Therefore, we use pairs of task and solution to create prompts and desired response for supervised fine-tuning. Once the LLM has a substantial knowledge about the domain, we provide a specific student context to the LLM in order to model the student. And in general, the student context can contain any information about students, such as background, learning history, problem-solving attempts. In our work, we provide this context in a triplet of reference task, solution, and the student code, as shown in the previous slide. LLM have been shown that they can effectively learn from such contextual information without explicit training or further parameter update, which is known as in-context learning. We evaluate how our method instantiated from proposed framework perform on the existing student scene benchmark created for benchmarking student scene synthesis method in our code challenge. This benchmark has a total of 36 evaluation scenarios. The synthetic dataset of task and solution are used for fine-tuning LLMs to provide domain knowledge. We ask experts to annotate the quality of generated student attempts using the following quality rubric. The first metric is Q2 measuring whether the generated student code captures the student behavior. The second metric is Q task, which measure whether the generated student code captures the target task. And Q overall is the product of Q2 and Q task, measuring whether the generated student code captures both the student behavior and the target task. These metrics have real scale values. We compare our framework with baseline method from existing work. The first baseline is neural SS, a long short-term memory-based neural network pre-trained on expert data and continually trained on real student attempts. We also compare our framework with human tutors in the visual programming domain, referred to as tutor SS. Based on our framework, we developed the following concrete methods using base model of GPT 3.5, GPT-4, Llama 2 7 billion, and Llama 2 70 billion. models with and without fine-tuning. This bar chart shows the average Q overall score, which measures whether the generated student code capture both the student behavior and the target task. On the left is the result for the reference task out of code maze number 4, and on the right is the result for the task out of code maze number 18. We draw the performance of human tutors by the red dashed lines, which serve as the performance upper bound. Green area correspond to the improvement by fine-tuning on expert data, and arrow bars computed over several fine-tuning runs. So without fine-tuning, our method based on GPT-4 perform best in both reference tasks and surpass the baseline node assets. By looking at the green area, we can see that fine-tuning boosts the performance of our method significantly. And this means that providing expert knowledge to an LM helps improving its capability in modeling a student and synthesizing the student behavior. Remarkably, in that task, our code maze number 18, our method using a fine-tuned GPT 3.5 model can reach very close to the performance of human tutors. To summarize, in this work, we propose a novel LLM-based framework for in-context student modeling and in open-ended domain. Evaluation results show that our framework achieved good performance on visual programming benchmark with a significant improvement by fine-tuning. There are several interesting directions for future work, including evaluating our framework in other open-ended domains and also to see how it helps in downstream applications. Thank you for your attention.